I am a postdoc at Purdue now. I'm joining UTD in the computer science department in fall 25, hopefully in August. So I'll just get started into the topic. So I work on 5G security, technology that everyone uses, even though they don't want to, but they have to. So I'm going to talk about systematic security analysis of 5G specifications and implementations. But since this seminar is on AI and ML, I'll be focusing on different learning techniques. Some everyone knows. One that not many people uses, but that is also a form of learning technique. So I'll get started. So cellular networks, 4G, 5G, it has been daily used by around 7 billion people with a lot of 800 plus operators with 170 countries. Apart from the general use case, which you know, phone call and internet, it is used for IoT, autonomous vehicles, supply chain management, autonomous healthcare, and much, much more. So with such an important technology, we have to make sure that the protocol specifications and implementations both are secure and don't have any security and privacy issues. So that is where I'm going to talk into. But just as a retrospect, we hear about all these Gs, right? 1G, 2G. So what are these? So these are different cellular generations, which started from 1979, which is 1G. Then we started having every 10 years a new iteration. So we had 2G, 3G with circuit, voice, and packet data, 4G with a lot of improvements. Then we have 5G. Now we are talking about 6G in 2028. But what in terms of security? So as any system, 1G, 2G didn't have any security because security was an afterthought. But with 3G and onwards, we are trying to provide authentication, better encryption, different schemes that we can provide. Now we are talking about resiliency, which is a more critical problem than security itself. It is reliability, adaptability, and security. And we are saying that the protocols in the future will be secure by design. That means like if we design a protocol, all the implementations will be secure if they follow the protocol. So this is the critical question, are cellular networks 4G, 5G secure? So I think everyone can understand that if it was secure, then I would not have been standing here talking about it. So I will just go into the most interesting thing that I like about my research, which is attack demos. So I really like to show attacks. Some say I like to frighten people, but just to show, I think attacks have a really good impact. So for this, you can see this is a small USRP, which are software-defined radios, which are very cheap, like $1,000 each, which we can use to carry out different attacks. So the attack that I'm going to show is called panic attack. Basically, with this attack, the attacker runs its script, and with this universal radio, I will send broadcast messages that will create this sort of a prompt on everyone's phone. So you can see the impact. So when I was designing this talk, at first I thought to do this attack live, but my advisor said, don't do that. You will get into legal issues. So, but the impact is evident, right? Suppose there is a big soccer game. I have this set up in my backpack, and I just create this attack. Everyone gets this sort of a prompt. They panic, and that creates a lot of chaos. So that is the problem, right? The essential question is that this is a known issue. I know that. Now you guys know that. Then why this exists? So that comes to the next part of my discussion is what are the challenges in ensuring the security and privacy in cellular networks. So the first one is this design is based on complicated and huge standards, which is done by a standardization organization called 3GPP, who designed these standards, writes them in English, and based on that, implementation vendors actually, whoever wants to deploy this, they have to create the protocol implementation. So you see the first problem, right? The specifications are huge. They don't have a formal model. They are under-specified in separate, different scenarios. I'm going to talk about more problems about them later on. But this is kind of the root cause of a lot of issues. The second is overlap and backward compatibility. So suppose I create a new version of a protocol, 6G, entirely secure. Still, I have to support 5G, 4G, 3G, 2G, 1G, because that is how the system is designed. So we and other researchers pushed quite a lot to kind of reduce this backward compatibility. And now if you go into your smartphone, Android or iPhone, there is a manual option where you can stop going into 2G. Still, they are not willing to stop 3G altogether, because at the end of the day, this is a business model and a lot of things. The third one is unpatched design vulnerabilities, the one that I showed in the previous slide. So there are quite many unpatched design vulnerabilities that everyone knows in this ecosystem, but they are not able to fix because of several issues that I'm also going to talk about. Lastly, the implementations are stateful and complex. There are a lot of problems in implementations that create a lot of bugs and vulnerabilities. So due to all these reasons, securing 4G and 5G is a tough problem. And I, over the years in my research, have tried to tackle this problem in different directions. So I do a lot of formal analysis. That was my PhD. But I also went into applying NLP and machine learning for a lot of these problems. So for this talk, I'm going to focus on 3 bits and pieces of my research, going into some attacks and some defenses as well. So I'll jump on to the first concrete problem, which is inconsistencies in the standards. So as I mentioned, the standards are huge. So there are inconsistencies in the standard itself. So if you have an inconsistent standard, then there is no way for implementation to be secure, right? Because they don't know what to do. Just giving a concrete example. So these are 2 prompts taken from 2 different specs. So these specs are designed by 3GPP, as I mentioned. As you see, the precondition on both of them are same. So both says if you have received a message with cost 14, but the action is different. So this talks about transitioning to a state. This talks about transition to a different state. So what the implementation design would do, that was kind of the main theme of this research. That is it possible to develop a systematic framework to identify inconsistencies and see how these inconsistencies actually react. Obviously, it cannot be done manually because the specification is huge. And at that time, large language models were a good idea to apply because they understand the natural language encodings, and this is written in English, right? So what at the end we went for designing is a large language model-based framework to detect this sort of inconsistencies in 4G, 5G standards. So for next part, I will just go directly into the approach, see the framework and tool that we designed, talk about some results and some testing. So what happens? We have this 3GPP specification. So the first part is very simple. We basically segment them into different paragraphs, which we can use to kind of do this inconsistency checking. We call this context-preserving sequencing, very straightforward. But here comes the first challenge. We want to use large language models, but large language models are not domain-specific. They don't understand 5G jargons. 5G has a lot of jargons, like any specialized field. So how can we deal with that? So we actually partially solved this problem with a previous work. We created a large data set for 5G to be used with large language models, which we call Spec 5G. So the idea was very straightforward. Use Spec 5G to do MLM pre-training, then your model will start to understand the 5G jargons. At the same time, we created embedding vectors from these context-preserving sequences. I'm going to talk about why we need these embedding vectors in the next slide. So here comes the second challenge. How do we know where to look for inconsistent pairs, right? So we kind of took the spec, we made it into segments. If we try to compare one-to-one between all the segments, life will be hell because there are around a million of these sort of comparisons that we need to do. How can we solve that? And the next challenge is how can we formulate this problem with large language models to detect inconsistencies. So this is where actually, at least to me, the most interesting idea of this paper is, so what we actually went with is a very simple idea. So if you have 2 segments, right, and they are talking about totally different things, then you don't need to compare them, right? Because they are talking about something very different, and it is very unlikely that they will be inconsistent. Similarly, if you have the segments which are absolutely same, you don't have to compare them because they are most probably not inconsistent. So the idea that we went with is using those embedding vectors that I talked about, doing a cosine similarity checking on top of that. You check the similarity. If the similarity is within a certain threshold, you keep that. If it is lower a certain threshold, you throw it out. So just to show, we tried with different embedding vectors, and at the end, we decided with TF-IDF because it gives the most sparse embedding that we wanted to kind of reduce the search space. So just as an example, how much reduction we could cause. So this is the similarity matrix, both in 4G and 5G. You see the dark spots are basically things that are talking about different ideas. So we don't need to compare them or take them to the next step. We only take the brighter spots in this search space, essentially reducing from million comparisons to 1,000 comparisons. So now the next part, how will we use large language models to detect inconsistencies? So for that, we actually formulate our problem to natural language inferencing task, which is a known task in NLP, which basically says whether two sentences are entailing each other or contradicting each other. So we use the large Stanford natural language inference data set to kind of train our model. So at least it understands what inference means and inconsistency means. But still there is a problem. We still haven't shown any ground truth for supervised training in the context of 5G. So we have to do some annotation. So for annotation, we actually followed the SNLI scheme and went with 3 different groups. So red is contradiction, green is entailment, and blue is neutral. So for our annotation scheme, we actually went with the active human in the loop annotation idea, where 3 experts, each with 150 annotations, will be looking into the results and fixing whether there are issues or not. So we create a ensemble transformer model based on different transformer models that we had at that time. Using a majority voting gives you the right result. So after all these steps, we got the output. But now what? We have to test it on real smartphones to see what we found actually as inconsistencies. So at the end, this is the end-to-end framework where we started with specification documents, and we were able to detect inconsistencies. Now the fun part, actually, the results. What did we find, actually? So we found, for model performance, we went with 3 phases. At the end, we got around 82.7% accuracy. For inconsistency breakdown, we manually looked into the inconsistent segments, both in 4G and 5G, grouped them together into different security problems and issues, totaling to 157 inconsistencies that we reported to GSMA. Now, for finding 6, the first finding that I already talked about, if you have the same precondition but talking about different post-condition, that can cause issues. The second, so just as an example, how this was handled in open source implementation, as you can see, the implementation tried to be consistent and tried to implement both. So in line 3, it tried to go into a separate state. Line 7, it tried to go into another state. So basically, line 3 is kind of a dead code because that will never be executed. For some other inconsistency classes, these are from 2 different specs, one from the security spec, one from the system spec. So from the system spec, it says that there are certain conditions where you should not protect messages. But in the security spec, it says you should protect all messages. So you see the inconsistency, right? What the implementation would do, where you have this sort of conflicting or inconsistent spec provided to you. The third group is so NCC, NH, these are very important variables that has to be different every time. So in security spec, they say that it has to be fresh and belongs to an unused pair. But for the system spec, it just says it can be different. So from a security point of view, these are very different specs provided, and one is secure, one is not. The last one that I want to show is different parameters. In one case, they say we have to delete all of them. In another case, they leave some of those parameters undeleted. So these also creates a lot of problems. So from testing point of view, we actually tested 21 devices. So the main outcome that I want to highlight is we found different things, right? So first of all, in some cases, all the specs, all the implementations, they basically followed one type of spec, and indeed that spec was secure. In another cases, all of the implementations, mostly all of the implementations, tried to follow the spec which was secure. In some cases, some did secure, some did unsecure. So this is what we wanted to show, that if your specification has inconsistencies like this, then people will implement different things in different areas, ranging from the most unsecure one, the most secure one, and in between mix of both. So this is the first part. So we created a framework called CellularLint. We detected 157 inconsistencies from around 6,000 specs. I'll stop right here if you have any questions. But one question that I get all the time, because this was done before ChatGPT was popular, so I get this question always, that what happens? So yeah, we get that you did the search space reduction and you have those sort of pair of segments. Do you need a specialized model? Why can't you just give the pairs to ChatGPT and ask ChatGPT, are they consistent or not? So actually we tried that experiment. What happened is some cases where the inconsistencies are very evident, like the first case that I talked about where the action is different. ChatGPT says, yes, that is inconsistent. If the inconsistency is very nuanced, then ChatGPT says there are no inconsistencies. In some cases where there are no inconsistencies from our end, ChatGPT says there are inconsistencies. So the result varies all across the board. This shows that yes, ChatGPT is nice, but still you need this sort of domain-specific large language models to be able to reason about very specialized tasks. You cannot reason with ChatGPT in those ends. So if you guys have any questions on this part.
Just a clarification. So for your grant work, you said that you use majority voting and then you put a human in the loop?
So yeah, so the model uses majority voting, but for the active human in the loop, we annotated 450 of those sort of segments.
And then you trusted the LLM for the rest?
Yeah. We trusted the LLM for the, after 450 annotations were done, we trusted what the LLM.
What was the accuracy of that 450?
So for that 450, because there was a human in the loop, if there were some issues, the human would fix that.
Yeah, but what percentage of issues did you have?
That's a really good question. So actually, we didn't track how much the human fixed. But at the end, when we left to the human, it was like around 83% of accuracy.
So that could tell you how much you can really trust the LLM.
That's a really good comment. Yeah, we actually didn't think of that.
And then one other thing is that when you compared the cosine similarity of the embeddings and then you concluded that those that were not close, they probably were talking about different things, couldn't it be because of like a very large inconsistency that they were not really similar to each other? So by dropping them, you would lose those samples.
That's a really good comment. So yeah, definitely we are sacrificing completeness to a certain extent. We are mostly focusing on soundness. And from our personal experience, 3GPP specs are bad, but not that bad. So we were mostly confident that they will not have inconsistencies with such a huge depth that there were no similarities, but still they are inconsistent. So this is kind of some domain knowledge that we had in this area, that we concluded that yes, even if there might be some missing inconsistencies, we should be able to get most of them. So at the end, we fixed a similarity score of 0.7 or 70%, which was enough to get kind of really good results for us to show.
Maybe one alternative, you could also use topic modeling. Did you try those?
Not yet, but the thing is that we are trying to. So when I designed this approach, the idea was this should be generalized for any wireless protocol. So we are actively working on now this to apply on Bluetooth. So definitely we will look into topic modeling and more sophisticated approaches to enhance this framework. But for this project, we didn't look into topic modeling.
Very nice.
I have a question.
Yeah, sure, go ahead.
So
Yeah, 0.7.
How do you end up with 0.7?
So that was bit, so there were few considerations. We didn't want to end up with a huge number of, because at the end, there is some manual effort, right? I didn't claim this as an automatic framework. I claimed this as a semi-automatic framework, right? So we didn't want to have so many pairs that at the end, the manual effort was too much. So we kind of assumed a balance between the search space reduction and how much manual effort we needed to do. So 0.7 was kind of a sweet spot with around 6,000 pair of segments that we could analyze.
One more question. So you fine-tuned the model. Is it BART-based model?
This is a BART-based model, yeah. So we actually, at that time, so this research was done back in 2023. We did GPT-2, BART, Roberta, and ExcelNet, so which were kind of the big models back then.
And you use 3 model and then use ensemble?
Yeah, we use 3 model and an ensemble of that. Yes, please.
One only short question. I think you answered that, but sorry, I ask again. You used some embedded generator like Portobag and so on to generate the vector and find the similarity between them. But my question is that you just use them only for finding the similarity, or use them as generate something for training the model as input of your model, right?
So for now, that is only for the space reduction, just for similarity. We didn't use that for any other task. So the current application for that is only to reduce the search space from million segments to kind of 1,000 that we can listen.
So how you train your model based on what kind of features?
So for the first pre-training, it was mass language model pre-training, because we created a data set where you understand like the specs. So that was the first part. Second is based on the annotation, right? So there was a label 0 or 1 based on whether this is a inconsistent pair or it's a consistent pair.
Okay, so I have like 4 questions. So for the first demo, I see in the demo, in the implementation, E node B, not G node B. So you was like running this for the 4G network? So
this specific demo is on 4G network, but we have also verified that on 5G because nothing has changed.
Yeah. But have you implemented it?
Yeah, we have that. We have that with G node B now.
Okay. And what's the difference that you noticed between E node B and G node B?
The USRPs become costlier. Yeah, because for 5G we need to use a 310. So for this we use B210s, which cost like around 2,000 each. But for 5G we use X310s, which is like around 9,000-ish. So 5G test beds are a bit costly. Other than that, we didn't have to do that much effort.
Yeah, I mean, from technical perspective, have you noticed any like difference in terms of like the accuracy or like?
So because these are mostly broadcast, so if you broadcast with high enough signal strength with high enough messages, what we found the impact is same. But yeah, because unless you provide some sort of a authentication there, we don't seem there would be much difference, right, from a technical point of view.
I have the second question is about the data sets. So do you have like any examples of the entities of the data set? So you said you built your own data set, right?
Yeah. So for the spec 5G data set that we created for like large language model training, it's kind of a data set from the specification and scraped from the internet. So this is just a huge text file where we have pre-processed so that we can use that. So all of this is public. So the data set is public. And even for this project, everything is public. So we publicly provided the data set, the models, and everything.
Yeah, but what are the entities that you collected in these data sets?
So in terms of entities, you mean like from UE, GNodeB, this sort of entities, or?
Yeah, I mean, when you collected this data set, you collected like some data from the user equipment, GNodeB.
So this is the standard data set, right? So we actually collected data from the 3GPP servers where they talk about the protocol. So this is 3GPP's design of the 5G protocol. So we don't actually scrape any information from UEs or GNodeBs. So this is just English language text describing how the protocol should be done.
Yeah, and you refer to like I think data set like Stanford data set or something?
Yeah, so for inconsistency detection, Stanford has a SNLI data set, but that is not related to 5G. That is basically a data set that people use to detect the entailment of two sentences. So the idea for us is we use that data sets to formulate the problem to a SNLI, like natural language inference problem, because there is some similarities, right? But it doesn't understand 5G. That is why we have to do the active human in the loop annotation scheme with 450 annotations that we manually did.
Okay. But in somehow there is no like any link between the Stanford dataset and your.
There are no links. So basically, the underlying assumption is that the SNLI dataset also is written in English. Our spec is also written in English. So if we fine tune with the SNLI dataset, the model should understand better what entailment and inconsistency means. Then when we put into the domain specific dataset, it will give more precise answer. So to summarize, there are three trainings, right? First is the fine tuning that we did with the large 5G dataset to make sure that it understands what 5G specific jargon is. Then the SNLI to make the model understand what entailment is. Then the find specific domain specific dataset to figure out 5G specific inconsistencies.
Okay. And I think in slide number 24, you refer to like the fresh and belong to unused.
Yeah, I think you are talking about this one, right?
Yeah, this one, yeah. So, yeah, what do you mean exactly by this?
So let me explain. So actually we looked into different implementations, open source implementation. So when I say fresh and belongs to an unused pair, that means the implementation has to make sure with the array list or something that these parameters are never used throughout its span, right? So that is what we expect to be a secure implementation, because if you use the same parameter twice, that will cause a lot of issues. But when they say that the NCC value is different, then the implementation basically is a check, just seeing whether the previous value is equal to the current value. If it is not true, then the implementation is fine. So you see the problem, right? We can do a lot of replay sort of attack in this second scenario, but the first one is replay proof, which we expect the implementation should follow.
Yeah, and when you refer to the key KGNB, this key represent part of what, the authentication?
So this is part of the G-Node B's key. So after the NAS layer authentication is done, this is the base station master key that is created from the NAS layer authentication key after the 3GPP 5G AKA procedure is done.
Okay, and this is part of like the authentication process?
Yeah, this is part of the authentication process where
between
these.
the user equipment and the G-Node.
Yeah, this is between the authentication, between the, so not, yeah, the authentication is between the UE and the core network, but through that authentication, you create keys for your G-Node B and UE, right? I'm talking about that process where you should use different values for NCC and ANH, making sure those keys are always different.
And last question in the last slide, actually, 43.
Yeah, sure.
I think I should start with this one, actually, because it was there already. 43.
This one, right? Yeah.
Yeah, so you refer here to like 4 security critical categories. So what are the security critical categories?
So the 4 examples that I showed, first one is mishandled state transitions that causes problem. Second one that I showed is basically kind of issues related to encryption and authentication. Third one, that the NCCNH that you mentioned, issues with parameters. And the fourth one was actually tracking variable values. So these are created by us to clearly demonstrate the issues. So this is manually created by us from the issues that we found. So I didn't go into the detail, I just showed one example for each.
Yeah, and in these examples, have you like run any like real-time attack and you like injected like real-time malicious data while you are running?
Yeah, so all these attacks are done on the phones. The phone that the list that I showed, we verified these attacks on the phone. Otherwise, it's hard to convince nowadays top-tier conference reviewers, you know, right? So that is a big part.
You implemented this at the user equipment.
Yeah, we didn't. I think I'm getting what you are referring to. We didn't tested anything on the core network side.
Core, yes.
Yeah, because we don't have permission, right?
Yeah.
Yeah, we actually, for the core network side, we showed the issues on open source implementations, but we couldn't show the issues on commercial stuff. So we had to rely on smartphones, like issues on that end for the commercial.
Yeah, the reason why I'm asking this actually because here we have some work on the G-Node infrastructure. Maybe after the presentation, I will show you something in the lab.
Yeah, definitely. If you have Amarisoft, you can kill Amarisoft.
Yes,
that is enough.
We have the American whole box as
Yeah. That is enough to convince reviewers nowadays.
Yeah.
But yeah, we don't have Amarisoft. Our lab is poor. So yeah.
We have the expensive one, so you can use it.
Yeah, so I will move. Thank you for the question. So I will move on to the next part. So I talked about issues in the specification. Now I'm going to talk about issues in the implementation. So I actually included this work specifically because it also talks about some sort of a learning, but not the learning that we are used to. I'm going to talk about a different learning that is used in programming language community, which is called active automata learning. So I'm getting into that. So the idea that, let us assume for a second that specifications are nice, they are secure, they don't have any issues. So even if you have no issues in the specification, implementations can deviate from the specification. They might create issues that would be exploitable or that will have sort of like interoperability between different operators. So for this, actually the research question was, is it possible to design an automated black box protocol analysis framework that finds this sort of non-compliant behavior on implementations? So for that, we actually created a framework called DIQE. So DIQE is the Greek goddess of justice, and UE is the user equipment. And my advisor is Italian, so people ask why I named this DIQE. So just to have a correlation. My advisor loves Greek mythology. So the idea basically is that suppose we have different smartphones. We want to test these smartphones, and based on that, we want to find this sort of non-compliance instances. So the high-level idea that we went with, if two implementations, they deviate from each other, then at least one of them has some problem side. This is kind of the high-level idea of differential testing. Both of them might have issues, we don't know. But if two implementations are deviating for the same input, we can confidently say that at least one of them is deviating from the standards, or the standard is unclear on that aspect. Otherwise, this sort of deviating behavior would not happen. So based on this, we actually create this framework where we use the access of different smartphones and detect this sort of non-compliance instances. So for that, we actually have to do two things. First is we have to create an abstraction from the implementation, and we have to check those abstractions in some way to find this sort of non-compliance instances. So for this abstraction extraction, we use an approach called active automata learning. So what this active automata learning does is, through a module that we created called FSM inference module, it communicates with all the smartphones by sending messages over the air. And with the response, it creates sort of like a formal model out of that. So this is a innovative symbolic learning technique that is just kept within the PL community. So the problem with, like, the difference between normal machine learning and this is that this is deterministic. So the model is not like probabilistic like machine learning models, but it gives you a deterministic model that you can use to test different things. So we apply this approach to all the smartphones that we have, create this sort of milli machines, and then we take these milli machines and design an equivalence checker module based on model checking of safety properties, and we pairwise check all these models that we created and find deviating traces. So as I said, the deviating traces are kind of a proof that at least one of the implementation is deviating from the standards, or the standard, at least in that place, is under-specified. So I will go into different parts, how this FSM inference work, the equivalence checker findings, and summary. So for this FSM inference module, the idea, as I mentioned, active automata learning, where the learner, which is a module or a software, it sends a bunch of queries, which are kind of packets. And based on the responses, it creates a formal model out of that. So at least when I first read about it, I thought it was magic, right? Because you send certain messages, you get the response, and you say, I got a model. But life is not so straightforward. Whenever you drop this abstract context, like abstract device, and put actual smartphone, then life becomes a lot complicated. So the first complication is you have to create sort of like an adapter thing, which is a large engineering effort. What it does, it takes the abstract symbol from the learner, creates a concrete packet, similarly gets the concrete packet from the device and creates the abstract learning symbol that we want to go with. So there are a lot of challenges applying active automata learning in the context of 4G and wireless protocols in general. I'll not go into detail of all of them. This ranges for what are the prerequisites that you have to mention. You have to balance termination and coverage. Because it's so powerful, it usually takes a lot of time. And the adapter that I mentioned about. I'm going to talk about just one idea, how we improve the termination and coverage balance in this case. So as I said, for active automata learning, you have to send a bunch of messages, right? So a message can be that you send a reject message, which kind of disconnects the phone, and then you send an authentication request, right? So what happens, you already disconnected the phone yourself, then the authentication request is mostly useless, right? So we use this idea. Basically, we check the context before sending the message, reducing the number of queries you need to learn the finite state machine. So we create different invariant sort of context. First is you have to establish the connection before sending a message. For every replayed message, you have to send the original message. And definitely for any protected message, you have to have the integrity and encryption keys. So the idea is you check the context before sending the queries. If the contexts are violated, you don't send the queries, save your time and effort, right? So using this FSM inference, we create this sort of finite state machines. But next part is how we are actually going to find deviations, right? So we have these two finite state machines. The easiest approach is take a model checker. Basically ask the model checker whether for the same input you have the same output or not. If the model checker finds the issue, it will give it to you. But the problem is that we did all this effort not to find one deviation, right? We want to find a lot of deviations. So our goal is to discover many diverse deviation inducing traces. So I will show this issue. So we have two finite state machines, right? So if we run the model checker saying like for every input, the output has to be different, we can safely assume the input would be a rectangle, then a triangle, then an arrow, right? I think everyone agrees this is the deviation. But if we say, don't give us this deviation, give a new one, what the model checker will most probably do, it will give you a rectangle, then a triangle, then followed by another triangle, and then give you arrow. So from a model checker point of view, this is different, right? But we know that it exercises the same thing, which we don't want to do. We want different deviations so we can find issues from there. So to resolve this, we actually create a concept of diversity class and deviation inducing inputs. The idea is instead of reasoning about input, you're reasoning about outputs. So you ask the model checker, give me an input where the outputs are 1 and 2. Similarly, you ask, give me an input where the outputs are 2 and 3. So for 1, 2, and 3, you have 6 different classes, right? So for each classes, you will get at least one of the input. So the idea is you get different deviations that you can use to find find non-compliance behavior from different implementations. So I'll move on to findings. So we tested 14 devices from 5 vendors, all the different vendors that were possible, all the different chipset vendors that we could get. We found actually 15 deviating behavior among all these implementations. Among them, 11 we could exploit. 2 we found interoperability issues. For 2 we actually couldn't find a threat model. So we can say that they are doing different things, but we could not exploit them, but we still reported in the paper. The issues that we reported stemmed from location tracking, denial of service, security bypass, broken encryption, all sort of things. So I want to highlight one issue that we found on Qualcomm that was patched and that was kind of a very interesting problem. So we have the smartphone, we have the core network, the security context has been established. There is a message called GUTI reallocation that, so GUTI is a temporary identifier. The high level idea is you should change GUTI all the time, right? Because otherwise people will be able to track you. So what we did, if you replay the basic GUTI message, it is not accepted, which we all agree is the right thing, right? I know this part might be a little bit boring because this is not machine learning. But yeah, this is some sort of learning, so it's interesting. So, but the interesting part is that for Qualcomm implementation, they accept another replayed message, which is called security mode command replayed. Interestingly, after that, it accepts all the replayed message. So what happened here? What essentially happened is, due to this replayed security mode command message, the implementation went to a certain state. After that, all the replayed messages got accepted. So this kind of is an interesting thing because this is a stateful vulnerability. And if you apply general software testing approaches like fuzzing, basic symbolic execution, you have a high probability you will miss that. And exactly when I disclosed this to Qualcomm, they said they heavily fuzz their system, which shows that why we need more sort of stateful vulnerability detection approaches to be able to detect this sort of very weird corner cases that has a lot of impact. So just a root cause analysis, we see that the implementation is doing something wrong because the specification said that you should not accept the same message twice. So I actually included this slide because the 3GPP folks said that I always say negative about them. So this is just a homage to them that they did the right thing. It is not their fault. This is Qualcomm's fault. So moving on. So just as a summary, so we created a automated black box tool, which is called DieQV. We found a lot of issues, bug bounties and CVs, all those sort of things. Any questions on this aspect? Okay, then I will, yeah, please.
Everyone has a question, yeah. Just if you can just go to, yeah, if you just go to the, yeah, like, no, the identification scenario, I think it's 68.
60.
68, yeah. Where you stop is the
Yeah.
secure, the secure context. So, what do you mean by the security context established here? This means that both of them are authenticated to each other?
Yeah. Both of them, the authentication, the registration process is done.
Yeah, but if the security session was already established between both of them, how the root cause attack actually is injected here? And when you change the go-to relocation command, reply it or replace it maybe with some other parameters here. I mean, how the attacker is actually involved here if you have already a security context established?
So the attack basically saves this message, replace this message. So it's not changing anything.
So this is like a kind of like man in the middle attack here?
So definitely you can do it in man in the middle. I think a man in the middle would be the most proper use case. So I didn't show the attack scenario here. I just showed what is the problem. But yeah, definitely you can do man in the middle. You can do overshadow, whatever you want to. Pick your threat model. But the main issue is if you just take this message, save this message, you don't have to change anything. You replay this message, it's got accepted.
So it's a kind of replay attack?
Yeah, it's sort of like a replay attack. So the root cause is whenever they accept this replay security mode complete message, they kind of reset the counter to a weird value. That is what I understood when doing the responsibility disclosure with them. So the main root cause is some implementation issue with their sequence number handling. If they handle the sequence number properly, there would no case whether you can, after your security context is established, you have sequence numbers, right? So they should not accept any message with a smaller sequence number, but somehow they do.
Yeah, because what I'm trying to understand here is if the security context has already established, how the replay attack can be involved in the loop here, since both of them are already authenticated to each other, and the two entities are already trusted entities. Okay, so this can be actually done before this, during or before maybe the security context has been established.
So I think let's put it in a man in the middle scenario, right? So you have a man in the middle attacker in between. So you have the security context established, and it already saved this message, what it can do after in the man in the middle, because you handle both channels, right? You can inject this replayed command in between from man in the middle, and that will get accepted, right?
Okay, yeah, but okay, yeah, but in this case, the security context was not established. I mean, like
I get, so the thing
was compromised already. I mean, because if it is already established between both of them, you cannot involve the man in the middle or the relay attack, unless if you are already injecting some vulnerable points, like if you are already having like preparing the scenario where you have like some vulnerable points, so the attacker will use it, even if the security context has been established between the two ends.
so
Are you like supposing something like this? Or?
no, so for this we are not supposing any specific threat model scenario, but in the paper we showed that this can be exploited in different scenarios. But what we mostly focused on the problem of the implementation accepting replayed packets. But there are certain scenarios. I get your point. This would not be this straightforward. You will have to have multiple sessions. You have to save the message from one session, then replay that another. That, yeah, definitely there is some sophistication when you do the attack. But the aim of this slide to show that a implementation like Qualcomm, it is accepting replayed packets, which is a big deal in any way, right? Because no one should accept replayed packets in any implementations. Okay,
I think
yeah.
I didn't get so DIQ, do I say it right? DIQ,
Yeah.
DIQ application edit. So what do you do with this inconsistency? Does the deviation from each other implementation shows something, some weaknesses in the standards specification, or like how do you deal with that inconsistency at the end?
So there can be two scenarios, right? First is this issue can be from the implementation, like what we are seeing here. Mm-hmm. Then we report to the implementation, and it's up to.
No, but you cut this because of the deviation of the behavior of this device with another device.
Yeah. So
how did you define which one is different?
So that is the point, right? So that is why I emphasize that if for the same input, two devices behave differently, that means either one of them is wrong. Which one is wrong, that we don't know. Yeah. That we manually figured out. Or if there can be another option as well. Both of them can be different because the specification didn't specify. So yeah, there are some of those cases where we reported to the standardization folks that look, implementations are doing different behavior because you do not specify what to do in this case, in this scenario.
So the application of DIQ is like you check it's some given implementation with a set of standards and then report back to like the...
So the whole problem is there is no formal model of the standard, right? If there was a formal model of the standard, life would be easier for us. We will basically test whether implementations follow the standards or not. Since there is no formal model of the standard, we kind of circumvent that by doing a differential testing. So the idea is, when you don't have a formal model, how you find issues in both implementations and standards, you do differential testing, right? You basically figure out where they are doing different things, and that can lead to implementation issues or specification issues.
So, I have a follow-up question. So, you said you reported 60 CVs?
Yeah, around that.
What was that about? Like, it's like related to implementation and...
So the CVEs are for different implementation issues from different vendors. From standards, they don't provide CVs. So standard is you just report them to the standards.
So when you were checking the implementation, you also found some problems in the implementation and faults of those systems.
So as I said, the root cause can be one of the two, right? One root cause might be that the implementation is doing something wrong, where scenarios are like this, where the specification is very clear on what to do. So there the blame goes to the implementation. if the specification, manually we couldn't find any sort of like a root cause from the specification being vague, then we go to the standard and say like, look, these different implementations are doing different things. The specification is under-specified in this option.
But can the root cause be not the implementation of that specification, but some implementation somewhere else?
At least someone has to do a mistake, right?
What is it?
So I'm saying like at least someone has to do something different to be caught here, right?
Yeah.
So yeah, definitely there is someone to blame. So the good thing about this approach is you can definitely blame someone. The question is whom you want to blame. Either you want to blame implementation or if you want to blame the standardization bodies, because the assumption here is if we take the same spec, everyone implementing the same spec, the behavior should be same in all the scenarios, right? That is kind of the.
No, my question was more like, so your traceability between the specification and implementation, is it one-to-one, or is it the specification might be implemented in different parts of the software?
So our is, so we get the pairs. Our is to figure out why these pairs are different. So if we see the specification doesn't properly say what to do in this case, then we say the specification is wrong. If we can find some concrete thing where the specification says that they need to follow that, but the implementation too is different, we go to the implementation.
I have a naive question. So for the input and output data you're dealing with, how they look like for those who are not familiar with this?
So input and output are here is packets. So input is, so if we go back, so input here is some packet, output here is also some packet. So these are the UE and the core network, right? So the input would be some message that is going from the UE to the core network, and the output would be some message that is coming from the core network to the UE.
So given the same input, it is expected that we want to have the same output.
That is why the spec is here, right? The spec should mandate that. That is the assumption that I'm referring to, that we assume since these are implemented from the same standardization body, for the same message we should give the same output. When this doesn't happen, we started digging, and that is where the whole idea is coming from.
Yeah, and in slide 46, I still see that you are doing the work for the 4G LTE.
So this is from 2019. So yeah, definitely I have to say this is 4G. But
this one is implemented to the so the core network here is what? Is the G node B or the?
This is the E node B, but the like one of my mentors from this project, he also did this in 5G. So you will find the 5G version.
Scenario on the 5G
Yeah.
cannot be implemented.
Yeah. This is on 4G. You are definitely right. But yeah, the same approach goes for 5G as well, and that paper got accepted last Usenix. It's called 5G based checker, but it is also differential testing based on kind of the similar ideas. But I think that paper is interesting because a lot of questions that you are having on this root cause analysis, they try to address that in a better way. So it is more automatic root cause, where here everything root cause analysis is manual, right? Because after you, so what this framework gives you, it basically says for this same input, these two implementations have these two different outputs. That's it.
Yeah.
Then it's up to you to figure it out.
Yeah, because in the 5G model, actually, you don't have like a direct connection between the user equipment and the actual core network. Because
So this is MME actually. So when I say core network, this is MME. So this goes to the G node B. I haven't shown the G node B to better understanding. But for that paper, they actually found a bigger problem in Samsung phones. They accept a lot like worse scenarios. But yeah, the threat model, the idea, everything is similar. Right? So I will just move on because yeah, I think people are back getting bored. So the last part. So this is more like a defense. So I have talked about issues in specification. issues in implementation. The last part I'm going to talk about some defense to kind of resolve these issues. So one of the popular threat models in both 4G and 5G is fake base station. So the idea is that you have the base station or G node B that is connected your smartphones, but anyone can create this sort of fake USRP based base stations, and the only thing that is needed to connect with the smartphone is a higher signal strength. So you can create a fake base station with a higher signal strength, and your phone would connect with that fake base station. And this poses the question, are we connecting to a legitimate base station or not? And not only just base station, you can do a lot of different sort of attacks that has been shown by me and other people in the literature doing a lot of impact. And this is because there is a lack of authentication in initial broadcast messages, which I am still working on. So we have some projects where we are trying to provide this broadcast authentication between smartphones and base station. But it's a critical problem, because if you include a authentication here, it will provide a lot of overhead, which not everyone is excited about. Mostly core network vendors like T-Mobile, AT&T, they are not willing to. This is kind of a business model thing, so they don't want to spend their money on securing for this sort of broadcast messages. So this comes to the motivation that this is a persistent problem from 3G, 4G, and 5G. There is still no authentication between the base station and the UEs. There are billions of unprotected devices. Yeah, go ahead.
Yeah. So when you see that there is no like authentication between them, because there is like the AKA like.
AKA is between UE and the core network.
And when you refer to the core network here, what do you mean? Because the core network has like the pipe, like the G node B and E node B site, okay, and then the actual 5G for network slicing and the other stuff, the network function virtualization, software-defined network, and all this stuff is another core network. So which kind of, like, which type of things that you are referring to?
So let me explain. So so when you turn on your phone, right? So you get the RRC connection established.
This is antenna, right? This is a G node B one.
Yeah, this is the G node B, right? So basically when you turn on your phone, you send the SIB, MIB, you do the RATCH, and then you connect with the base station, right? So this is what I mean by connecting with the base station. After you connect with the base station, you have the core network site, which can be AMF for 5G. So after you connect with the UE through the base station, through the core network, you do the AKA procedure, right? That is what you are referring to, 5G AKA, authentication request and response. But what essentially we are trying to defend is this part. So if I create a fake base station, there is no one stopping me to connect your phones to me. Yeah, definitely I will not be able to complete the layer 3 authentication, but I would still be able to do a bunch of stuff due to this fake base station connection, because there are lot of messages that are not protected, especially reject messages, right? Attach, reject, authentication, reject, those sort of things that can create this sort of attacks. So that is what this project is trying to solve, the initial bootstrapping problem between the UE and the base station. Is it clear now?
So what I want to see here is that, yes, there is an authentication model actually between the user equipment and the G node B system. But yes, there are like some security issues when you open this kind of connection where you can inject like a fake base station in the middle.
Yeah.
But there are authentication models.
Yeah, that is in the later part in the process, right?
Yeah, like when you have like an IoT component connected, like smart car also connecting to the antenna, to the G node B, the smart car has to authenticate itself to the antenna, and the antenna then has to also authenticate itself to the smart car. So the scenarios already exist.
Yeah, that exists.
But there are some attacks. Yes.
Yeah. So that exists based on AKA, but that is kind of a backward thinking, right? After you do the 5G AKA, then you make sure that everyone at the bottom is right or not. But what we are essentially trying to see, as you mentioned, there are attacks. That is before you do the 5G AKA
and
part.
you are trying to exploit this kind of like vulnerabilities related to this authentication model.
Yeah, for this paper, we are actually trying to defend that. So this is the defense. There are a lot of papers that we refer to this paper where they exploit this. in here, our motivation is not exploitation. Our motivation is trying to defend this scenario. So that is where actually I mentioned that there are a lot of billions of unprotected devices due to these vulnerabilities that we are trying to make sure that we are able to defend. There are certain defenses already, but this always requires some sort of an extra module that you have to bring, and that provides like it is not usable for the general public, right? So our motivation was to create something that general people can use. So I will show one more thing, because these issues of fake base station, as Hisham is mentioning, these are not new, but just to show how prevalent they are. So this is the prompt that I took from January 10 when I actually did this slide. This is this year, January 10, where this sort of issues were being exploited to carry out different attack scenarios. So these are old, but these are always being exploited by everyone. So that was kind of our idea, that we wanted to create something that protects all the existing devices, that requires no protocol change, that doesn't have any additional hardware, that has minimal overhead, and that supports roaming, which is also an important aspect. So if I go to some other country, I still should be able to protect myself. So we actually face different challenges. I'll not go into all of them. First is we wanted to do something that employs machine learning, because there are signatures for this sort of attack. So previous issues or previous solutions that were based on static signatures, which could be easily broken. So we wanted to create some sort of a scenario where some sort of a sophisticated attacker can still be defended. So first thing problem is we needed to create a large data set. So we actually use the facilities provided by Powder. So Powder is a NSA funded big project in University of Utah, where we actually deployed this sort of fake base stations in the wild. So the reason is that we cannot deploy fake base station in the wild because it's illegal. If we do that, there will be problems. That is why we actually needed these facilities. Second of all, in our lab setup, we don't have this sort of large scale equipment, which in Powder we had. So we actually created a large data set that include mobility, fake base stations, different attacker levels, and different multi-step attacks that can be exploited. The second is this problem is interesting because not just the fake base stations, so this is kind of an intrusion detection system, right? But the main problem here is the issues are not in the packet. The issues are when the packet are being sent. So we need to be able to incorporate the surrounding context. So we created kind of a new sort of a model that is a bi-level model that does packet level classification and also trace level classification. So in packet level classification, essentially what we do, we use a stateful LSTM with attention and classifies each packet individually, whether they are from a benign entity or a malicious entity. The positives are it captures the statefulness of long-term dependencies, and the attention mechanism focuses on specific part of the packet. For the trace level classification, we actually got the packet level classification and use sort of like a binary classifier to classify whether they are basic attacks or some sort of a benign scenario. The third issue I'm going to talk about is multi-step attacks. So fake base stations are the starting point for different multi-step attacks. So for this multi-step attack recognition, we use actually graph-based models, which worked very well for us. We created packet flow graph based on graph neural networks, trained on them, and kind of classified the edges. Based on that, we could detect what multi-step attack there is. So I am just going to show a scenario. I think, Hisham, that would be helpful to discuss. So this is kind of a multi-step attack that can be done using fake base stations. So the idea is we have the UE and the core network, which is AMF. We have the G node B or E node B. Basically, you have the connection complete. A fake base station comes in. It sends the system information message. It completes the RRC connection. It sends a tracking area update. And for the fake core network or core network component, it sends a tracking area update reject, which is not integrity protected and ciphered. So that kind of creates a large-scale denial of service scenario that the attacker can create out. So now question is how we can detect that. So this is done by previous work. We didn't do the attack. What we did, we used these attack sequences to create this sort of like a graph out of that, and from that we created a graph neural network based model to be able to detect when this attack is being done. So overview of this fake base station scheme, we started with dataset construction, we created a machine learning framework, we are able to detect fake base stations and also multi-step attack. Some data that how well we did, we actually detected fake base station with 96% accuracy, multi-step attack detection accuracy around 86%. We also extensively evaluated this approach, so be able to deploy on real smartphone. So we did a big overhead analysis. We tested on real world evaluation as well. This is the most important part, like how we are doing when attackers are trying to reshape the attacks. So what I want to highlight is none of them are classified as benign. They might be misclassified in certain aspects, but still we are able to detect them in all the time. Similarly, for reshaped attack, we are always classifying them with the attack class they belong to. NSF actually acknowledged us because we are the first to use this sort of a large NSS platform to carry out this sort of a security scenario, which was really impressive. Last part, another demo. So this is basically the same 4G attack that Hisham mentioned, what I showed in the first. I will show how we can detect them now. So we have the attacker like similarly, but this time we have the fake base station detection app. And yeah, we will run that, hopefully. Yeah. So instead of previously where the attack prompt was shown, this time the attack would be detected and the app would prevent to show those sort of like a prompt. So now we can run the attack in background, like the detection app in background as well. At that time when I did the demo, we just have to start that. But the high level idea is if someone runs this app in certain scenarios, they should be able to detect themselves from this sort of known vulnerabilities that has been known by the community for quite a long time. So this is the summary of fake base station detection. We are actually working with a smartphone vendor who wants to deploy this solution on top of their baseband. So that's why we haven't been able to open source the app, but we plan to do so soon. So just as a disclaimer. So yeah, after this, I just have 2 more slides just as future work, just to highlight what I'm excited about. So 2 things that I'm really excited about is private 5G networks and non-terrestrial networks, which I am actively exploring nowadays. And on that note, yeah, we are coming towards 2028, so 6G specifications have been started. So I definitely want to contribute the resilience of next-G networks. So this is kind of a high-level overview of what I have been doing and the technologies that I develop and use in my research. In the future, I want to go beyond my research depth and research breadth as well. With that, I will stop if you have any questions. Thank you.
So for this work, I assume you are still dealing with the packet data, right?
Yeah. So
And what are the features? I mean, for in your LSTM model, I assume on each time step you have 1 packet, right? What are the features?
So we actually use a list of 200 features from the packets that we extract. So the specific list of features include what is the some of the important packet fields, the packet max, like whatever we can extract. So in the paper there is the list, but we use 200 features from the packets that we.
So you didn't use the raw data, you did feature engineering.
Yeah, we did some feature engineering. We didn't use raw data because raw data it was actually not performing that well. We had to do some domain specific feature engineering.
Okay, and how did you combine LSTM with the graph neural network model?
So LSTM, so these are 2 separate components, right? So one component with LSTM with attention that detects the fake base station, and another is the graph model that detects the multi-step attacks. So we don't actually combine them, but they are 2 separate entities just to be able to detect what sort of threat model and what sort of attack was done.
So graph neural network model is used for fake base detection.
So graph neural graph neural network model is detected for multi-step attacks. So fake base station is the root cause. So we actually detect the multi-step attack to more kind of understand what sort of attack was done. But yeah, fake base station is the root cause detection. This is morely to detect which multi-step attack was done by the attacker.
Okay, in the graph, what are the nodes and what are the edges?
So the nodes are basically, yeah, similar to what I showed. The nodes are kind of the packets, which packet, the order of the packets, as is, yeah. So these are basically which packet after which packet was received by the entity to the UV. This is kind of is used to create the graph.
And this is the sequence, the order?
Yeah. The order is when the packet is received based on that.
So, okay, so in this graph actually, because I know the multi-stage attack is like sequence of stages of multi-step here. So for each of this state, how can you define like the current status of your attack to define if it's like a compromisation or there is like a detection request or so? So do you have like a detection model or something that can actually define the current state of your system when the system moves from one state to another state in this graph?
Yeah, so we have actually, since we created the data set, we actually have some this sort of gold data set that we created. But yeah, definitely there, I get what your question is, because sequence can belong to some other attack to certain probability, right?
Yes.
So in that case, it shows which attack it belongs to with a probability class, and we assume the highest probability.
So you have here like a probability distribution when you move from one
Yeah.
state to another state, right?
Yeah.
And this data is publicly available or?
So this is publicly available now because we created this with Powder. So we kind of publicly made this available for people to actually, this was one of the big parts of this research, to make available this sort of attack data set which is not nearly available in our community, right?
Yeah, and what are the attack families that you have already actually used here in this data set?
So we had actually around 21 attacks. So one family, definitely denial of service. Second was location tracking. Third, we did some sort of like a battery depletion attacks as well. So yeah, these three are the big groups. There is bidding down attacks, which you can downgrade from 5G to 4G to 3G. So these four actually are the big groups, but we actually did for 21 multi-step attacks that we report in the paper.
And this has been implemented in the G node B in this case, or also in the LTE?
So this has been done for both 4G and 5G. For the current dataset that has been released, this is on 4G, but we are working on 5G as well with the Powder team, which hopefully soon be done within this quarter, hopefully. That is kind of the idea. Because we don't have actually physical access to the equipment, we have to rely on the Powder team from University of Utah to do some sort of a working environment for us.
And here you detect like a certain stage of the attack, but there is no like any kind of mitigation, right?
So
you just focus in the detection?
That is a really good question. So currently it's mostly on detection, but there are certain very minimal defenses provided. For instance, if the user wants, we actually leave this to the user. If the user feels that whenever they are being attacked, they want to get defense, they can put an option in the app that we provide that will turn off the radio.
So it's like a kind of like manual?
Not manual. They can just like, so we provide them option. Do you want to turn off your radio when you want to being attacked? If they say yes, then whenever they are being attacked, the radio will turn off.
Yeah, but in this case, you are just offering them like one just response.
Yeah, we were just saying like, save yourself, don't die. That is kind of the idea. But I totally agree with you. There can be more sophisticated defenses.
Yeah, because actually when you apply the mitigation, you end with like large number of responses. And
Yeah.
parameters when you choose which kind of mitigations that you are going to.
So that is what we are looking into right now, providing some sort of a defense.
We have this one. Actually.
Not detect. So that is something that we are looking into. But yeah, as you said, defense currently for our app is very minimal. It's just like you can. So I think we provide two options. First is you can detach from the current G node B and try to connect with some other G node B if it's present. do something like a blacklisting, or otherwise you can turn off your radio and say like I will be silent for a few minutes. I don't want to be attacked, something like that.
But you have two parallel networks, and then the LSTM based on the graph one. This one detects if it is a fake station. This one detects if it is a multiple state, right? And they don't communicate with each other.
So currently they don't communicate with each other.
Their input is the same.
Their input is the same. For current app that we provide, we only have the fake base station detection provided in the app. The graph-based one is mostly in kind of a prototyping state. We didn't deploy it to the Android app for now. So that the idea for that is mostly to do some sort of forensics to figure out what sort of multi-step attacks that people use and try to defend against those.
Yeah, just one last question. If you go to the network slicing part, I think the last slide, because this is actually what we are currently working on.
This one, right?
Yes, the previous one actually, the network slice. We refer to the network slice, yeah. So yeah, have you implemented anything like against the network slices here, or just?
So I haven't looked into network slicing problem yet, but as I mentioned to Joe as well, so we are part of a AI Edge Institute where there are certain people who are looking into network slicing quite a lot, more specifically from Northeastern. We do security stuff, so we plan to do some collaboration with them. You know, they have the Colosseum platform, which they use extensively for research.
Yeah, because actually in our lab here, we create like some network slices using the open source Mano and the Magma orchestrator, and then we kind of like try to compromise the network slice on the fly. And we have some demos actually. I think if time allows, I can show you some.
Yeah, sure. Network slicing is really interesting for us, but we don't have any specific projects running on that. But we have collaborators saying that we should work on that. So
Yeah.
I will look into.
So the previous work is for like for the network, like the let's say the 4G or 5G infrastructure as a whole, but not for the network slicing entities, like the containers running with the network slice or services running between like one entity to another entity, right? I know. Okay.
Yeah, we don't actually have looked into the security threats of that aspect. So that we plan to do in the future.
Yeah, I like actually this part.
Yeah, thank you. Any more questions? Yeah, please go ahead.
Did you compare the performance using stateful LSTM and normal LSTM?
Yeah. So we have a big, so for security papers nowadays, 7 pages are evaluation for a 13-page paper. Actual paper is 6 page, 7 page is just evaluating stuff. So there, whatever evaluation you can think of is in there. I am confident of that. Because that is where the community is moving nowadays, which is very odd to say, but it is what it is. Yeah, this got accepted to Usenix, so Usenix, you know, it is very hard.
And when you compare the performance actually, or like the accuracy performance, what are the metrics that you actually consider?
So we do the usual metrics like false positive, false negatives, accuracy, F1 score, everything.
Downsend?
Sorry?
The downsend model? Have you tried to use this one?
No, we haven't tried with that.
Because the downsend model actually help you to like link the false positive and false negative rates together, and then in this way you can compare it to like other people work even if you have like different infrastructure.
That's really nice. Yeah, I think we should definitely do that. So so a lot of evaluation that we did is why the false positives and false negatives were happening. So that is why one of the reasons for false positives and false negatives are the most sophisticated level of attacker who actually make sure that all the parameters are exactly the same and also send packets in the same order. These are the hardest for us to detect because the machine learning model needs some clues if you don't provide any clues. So that is why actually I write explicitly in the paper as a limitation that maybe because for this paper the data is only on the L3 data. We might have to go the lower layer data L2 and even L1 to figure out where those sort of anomalies are happening. But for L3, I am quite confident this is the maximum you can go.
So it shows that the LSTM success actually shows that the order of the packets are different. And
Yeah.
coming back from the state.
Yeah. Any more questions? Thank you.
Thank you so much for the fascinating presentation.
Thank you.
A lot of work.
Thank you.